Thanks, everybody, for coming. I'm here to share with you some ideas that some epiphanies that I've come to realize over a few years now doing Bayesian statistics and deep learning. And so this talk is going to be quite different from the other talks that you've seen. This talk is going to be centered on the math, but what I aim to do is to do the math without all of the equations, without all the symbols, and instead to convey the intuition behind some of the buzzwordy things that you'll see. I've revealed the title. In the title, I've revealed the take-home point. Machine learning is actually just curve fitting all the way down. And if you take home that point, and you're less scared of machine learning and more willing to approach it, as well as the internals of it, then I hope I've done something. I've got QR codes all over the slides and animations. Feel free to scan it. If you want to follow along on your phone or on your laptop, you can actually do so. I'm presenting basically from online. The slides are at this URL, my GitHub username, .github.io/curve-fitting-talk, or you can take your phones and scan the QR code, and you'll get a link to the URL over there as well. It might take a few moments to download the slides because it's pretty big. It's on the order of megabytes, and so the conference Wi-Fi is always going to be a bit congested. So just keep that in mind. Okay, so I just want to introduce myself a little bit. I currently work for the Novartis Institute for Biomedical Research, but I'm here at Digility for fun. The company is not paying for this trip at all. For me, sharing knowledge about statistics, computation is something I really enjoy, and I've done that at a number of venues. Inside Novartis, my official title is an investigator, which just means I do science. I'm not a software engineer. I'm more like a data scientist, but instead of trying to optimize how to get people to click on ads, we're trying to optimize medicines to cure people. And I'm on a team that's a really fun team. We sort of do all the high risk, high reward sort of stuff. High risk means high probability of failures. There are a lot of failed projects that we've tackled. But it also means we get to tackle some of the bigger problems inside the company at scale that our colleagues might not have the necessary manpower or time to support on their own. Prior to Novartis, I was at the Department of Biological Engineering at MIT. That's where I defended my thesis last year, 2017. So I've not really been in the industry very long myself, which is why coming to Digility is like a great thing for me because I get to see a lot of stuff that's going on as well. Finally, in grad school, I picked up the Python programming language. And as a language for programming, it's great. It's a good language for software development. It's very readable. It's not the fastest, and I think that's one of its limitations. But as a language for learning new things, it's a really good thing. It's a really good language. So I've basically been able to pick up all sorts of things like Bayesian statistics, machine learning, deep learning, network science, and incorporate them inside my research because the language, the Python programming language, is pretty well designed and good for learning these ideas. So I'd like to encourage you to pick it up. PyCon 2019 is coming up as well. It's going to be held in the USA. There are local PyCons that happen. So check them out. It's a great community as well. All right, so here are the goals of this talk today. Firstly, deep learning, AI, machine learning, right? These are buzzwordy terms that are flying about. It's right now at the top of the hype curve. What I want to do is to basically demystify deep learning for you and show that it's actually related to a long line of simpler statistical ideas that you probably have already encountered. More importantly, I want to do this with lots of pictures and minimal equations. Secondly, because this is a conference that is about AR and VR, there's a very strong design component inside here. So I would like to be able to show an example, at least one example, of how using a Bayesian approach to doing data analysis can help inform how we design applications, games, and programs later on. It's a very small example, but hopefully it conveys the message. Finally, I'd like to introduce to you a tool that you might be able to find useful in your toolkit, probabilistic programming. Right? It's a way of expressing Bayesian models in a way that's very intuitive with a language that is very easy to write as well. Okay? So those are my 3 goals today. Now, because this is a talk on Bayesian statistics, it has to include the obligatory Bayes rule slide. And so I just want to check in the audience, how many of you have seen Bayes rule? Oh, one, two. Two members of the audience have seen the Bayes rule. All right, great. So Bayes rule, I'm going to introduce Bayes rule to you. Bayes rule is a formula that lives as a neon sign in some, no, I'm just joking. Bayes rule is a formula that tells us how to update our hypotheses, our beliefs, having seen evidence, right? Put in plain language, that's what Bayes rule is. You don't need to understand what are the components of the formula at this point, and for the purpose of this talk, if you want to figure out what it's, learn more about it, there are lots of articles on the web that will show you what Bayes rule is all about. But for the purpose of this talk, you just have to remember, it's a way of updating beliefs, having seen new evidence, all right? Updating beliefs, having seen new evidence. What do we mean by beliefs? In statistics world, in statistics land, we express beliefs about the world using probability distributions. So you probably would have seen figures like this, like you know what the shape of the normal, the uniform, the exponential distributions might be. What exactly is a probability distribution? One way that I think about probability distributions is assigning credibility to particular values on the number line. That's all it is. So an example, the classic example we learn about is coin flips, right? And so we know coins generally are not biased, having flipped hundreds and thousands of coins in our lifetime. So when we want to assign credibility to the probability P of having heads, we'll put a lot of mass in the region close to 0.5. We'll put a lot of probability, we'll assign a lot of credibility there. And we'll assign less credibility, or even zero credibility, if we so believe so, to the more extreme values. So for the purpose of this talk, I'm just hoping that you know some things about the shape of probability distributions and what they mean. Things like the uniform distribution, which I'm mousing over here, they express that we want to assign equal credibility to every single value that exists on the number line. Things like the normal distribution express a different intuition. That is, I believe most values are credible in the central region of some of this distribution and less credible on the tail regions. Think something like the exponential distribution expresses this credibility assigned to only positive values of numbers, right? And that we have more credibility closer to zero and less credibility as we go out towards positive infinity. This holds for continuous distributions. It also holds for discrete distributions, and discrete distributions are just for integers, things that you can count. There's no fractional values involved. What's more important, though, is to know what we mean by the shape of a distribution and how that relates to the strength of a belief. So in this case over here, we have when we say we have a strong belief about a value, it's like the probability of having a heads when you flip a coin. A strong belief is expressed by a narrow probability distribution. That is to say, there are only a few values for which we are willing to assign credibility to. Whereas a weak probability distribution is sort of like very wide, right? We are willing to assign credibility points to many, many possible values. All right, having gone through those basics, let's start thinking about some of the elementary tasks that we do in statistics. So one of the first things that we do in statistics is estimation, okay? Estimation is one of the first things we do, and it basically starts when we have a bunch of data. Now, I like to think about data, I was inspired by one of my colleagues at work to think about data not as like numbers, but as point clouds. In this case, let's think about data in abstract as being a point cloud on the number line. So one of the things that we might want to do is characterize this data distribution. How would you do it? You'd say, well, what's the mean? What's some summary statistic? What's the mean? What's the variance? But when we start to express things like the mean and the variance, because this data comes from, is a sample from a bigger population of, or this abstract notion of what we would call a population, which reflects the true value of the things that we're interested in. Knowing the mean and variance lets us construct a probability distribution to describe that data. So, for example, human height, right? We want to know the population, we want to know the average height of adults in Europe, for example. So I'm from the States, right? I'm currently living in the States. We're in Europe. Let's use Europe as an example. I believe Germans are on average taller than Asians, and that should be a pretty obvious point. What is the average height of people in Germany? And so we would characterize it not by just the mean, but we can also characterize the spread or the noise in the data. And so we would express it not with a point estimate on like over here, but instead with a probability distribution. We're saying that most people, if we use the normal distribution to describe it, we're saying most people fall in some central measure of, around some central measure of heights. Very few people will be really tall. Almost nobody should be like 3 kilometers in height, and almost nobody should be 3 millimeters in height. That's sort of what we're expressing there. Now, if you're not colorblind, or if you are paying attention, you'll also notice I have 2 separate colors. So when we have a population of data and we know that there are subgroups, there are some estimation tasks that we can do is we can actually characterize each subgroup separately, right? And so that's sort of like the fundamental thing that you can do with data here. This picture here is actually the picture that I want people to get really, really familiar with, right? So when we talk about our data as being described by some distributions, that's the white probability distribution that's going to show up in every single picture going forth. We're saying that our data came from this normal distribution with a population parameter mu, which we don't really know, but we can estimate from our sample, and a parameter sigma, which again we also don't really know, the variance parameter, so how spread out things are. We don't know it exactly, but we can estimate from data. But how do we express that we are kind of unsure about the exact particular value of mu and sigma and other parameters? The way to do that is we say that that parameter mu and that parameter sigma, they each came from another probability distribution. Having not seen any data, we might assume as a naive thing to say, okay, it's probably a flat distribution, but having seen data, we would update our beliefs and say, it's not really that flat. Now it's a little bit more squished up because we've seen some data. And so now we know we have a bit more confident estimates of what this mu and what this sigma should be like. Now, if you can think about your data, this picture is actually what we would call a generative process for data. It draws out the generative process. That is to say, my data came from this normal distribution. It has 2 parameters. Each of them were, this parameter was drawn from that distribution. That other parameter was drawn from yet another distribution. This is what we would call a generative story for the data. So if you can think about your data in terms of a generative story for each of the key parameters that are involved, well then, if you look at code like this, written with PyMC3, the Python package, which is the probabilistic programming language for Bayesian modeling in Python, if you look at it, there's essentially a one-to-one correspondence between what you would draw for the generative model of your data and what you would write as code for fitting your data. And that is the most important thing that I want you to take back. If you can think about your data as being generated through some generative process, if you can construct a story for how the data were generated in a probabilistic fashion, then you can write PyMC code, Python code, that looks exactly, that has a direct one-to-one correspondence. So the mu comes from a normal distribution, the standard deviation comes from an exponential distribution. They are fed into the parameters of the normal distribution, which forms the likelihood for our data that were generated. Okay, so that's sort of the basics of estimation. Let's move on to another thing. Let's build on this intuition of sticking with point estimates versus going with probabilistic, what we would call probabilistic estimates, and talk about linear regression. So how many of you have taken a high school physics or undergrad physics class? No? Yes? Yes? OK, so some of you would have. If you have taken that class, one of the tasks that might have been involved is you would have some value x, and then you have a bunch of points on your graph paper, and they form a line, and you would just draw a line through it, right? So we would start with data that looks like that, and if you drew just a line through there, then you would essentially be doing linear regression. Of course, there's a proper formulation of linear regression, which is to find the line of best fit by minimizing the error in prediction. Well, that is a point estimate, and that just says there's one line. I believe that there's one line that fits the data. But if we were to do it in a probabilistic fashion, then what we're saying here is that it's not just a single line that fits the data. It's a family of lines, each explaining the data with different amounts of credibility, right? Is that clear for everybody? And so that's what we call Bayesian linear regression. And again, because we have two groups of linear data, we can do this estimation for each individual group as well. So this picture here tells us essentially what's going on under the hood when we do linear regression. All we're saying is I have my column of data x. It can be one column of x, or it can be 3 columns of x. If I have one column of x, I multiply it by one slope parameter, and I have an intercept parameter, and then I create my output value, which is the expected value. And we're saying here that, or if I have multiple predictors, then I just need to change the shape of my multiple slopes. And then I can basically say that my output data were drawn from a normal distribution centered on this mu value, which depends on the x value, and it's got some noise of itself. Put in terms of a picture, it just looks like that. The generative story just looks like that. So this is my data. This is the parameter mu. It depends on x. It's got 2 parameters. And because I want to express the uncertainty in that parameter, those individual parameters, then I say m is drawn from some distribution, c is drawn from some distribution, and I'll update my beliefs about m and c having seen new data. All right? So how would you write this with PyMC code? Essentially, there is a one-to-one correspondence with the picture. So m comes from a normal distribution, c from a normal distribution, the standard deviation, the sigma parameter, comes from an exponential. And we have this thing here which links the output over here to the x, the inputs, right? And then we put the mu inside there and SD over there and say that the data were drawn from a normal distribution that depends, whose center depends on the value of x that we've put inside there. And the dependence is expressed this way. Okay, so that's linear regression in a nutshell, Bayesian linear regression. So let's try logistic regression then. Logistic regression is just a way of trying to fit another curve that lets us predict whether, depending on the value of x, whether our y value should be a 1 or it should be a 0. And that's all it is, right? That's all that logistic regression is. So we can do the point estimate, or we can express it in a Bayesian fashion and say that there are multiple values of multiple curves, possible curves that express the data. Or we can do this hierarchical thing or this grouped thing where we say each group gets their own. So I'm going to focus again on this third panel over here. That's what happens with the math, right? So with the pictures that we're drawing, this sort of is what's going on, but I think it's always more intuitive to look at the generative picture as shown above. What we're saying here is that our data, which is a 1 or a 0, is Bernoulli distributed. And a Bernoulli distribution is a thing that takes in a parameter p and produces values 1s or 0s with the probability p. And over here, what we're saying with this function here is just that we have a parameter beta that controls how much, p depends on x, and there's a parameter beta that controls how slopey this curve is going to be. But what this really expresses with this formula is when x is small, the probability p will be small, and so we'll most of the time get 0s. And when x is large, the probability p will be large, and so therefore we'll get lots of 1s. And that's it. That's what you would call a link function inside your undergrad statistics class. This is how you would write it with PyMC code. And once again, don't worry too much about the code right now. You can always look at the slides later. What I want to emphasize, though, is that if you took any undergrad statistics classes, they would have taught you that this is called a link function, and they would have just left it there. Your professors would have left it there and not told you that any function actually can be a link function. Any mathematical equation that you can write that links your input data, x, to your output data parameters, p or mu or whatever, that's a link function. And that blew my mind when I realized this a few months ago, that, oh, yeah, any math equation can be a link function. It does not just have to be this. So if you don't believe me, follow this. We can do actually parametric curves. In physics undergrad class, you would learn about radioactive isotope decay, and it follows a curve that looks something like this. We can do it in a Bayesian fashion, and we can do it in a hierarchical or grouped fashion as well. So how would this work? Let's skip this one. Let's look at that. That's all that this is. We're claiming, right, in our model, that data are drawn from a normal distribution. The parameter mu is where the center of that normal distribution is going to lie, but it depends on the value of x according to this equation. And there's just a bunch of probability distributions that assign credibility to each of these parameter values, right? So if you know this particular data generative story, the PyMC code is actually really simple as well. The main point here is that if you have a probabilistic programming language in your toolkit, and you can draw pictures like this, there's a one-to-one correspondence between the picture and the code. And it becomes very easy to do your model fitting. All right, so then we go into neural networks, which is probably what everybody is wondering about. What is a deep neural network? Why is deep learning so hyped? Well, first off, we got to understand what a deep neural network is. We'll start with some data. And actually, you can fit data where y is only dependent on one value of x with a deep neural network. It's totally possible. You'll get some really weird curve fit. You can do it in a Bayesian fashion as well. You can also do it in a grouped fashion for individual data points. So this figure here actually tells you what is going on underneath the hood with a deep neural network. With a deep neural network, all we've done is we've taken our input data, x, and done a bunch of matrix multiplications against a weights matrix and a bias matrix, bias vector, to produce some output over here that we then subject to a nonlinearity transformation. We do this once, we do this again, we can do this yet a third time, a fourth time, fifth time, as many times as we want to eventually produce a deep neural network. And that is all that is going on underneath the hood. And along the way, what are we doing? We're adjusting the values of W and B's, the W's and B's, such that our predictions made from this model minimizes the error on against the actual data. That's all that a neural network is, right? And so what this means is a neural network is just a link function between your data and your output parameters. And that's all it is. There's nothing to be scared of about a deep neural network. One thing I do want to demystify here is a deep neural network is not generalized artificial intelligence. It is not. It is just a fancy curve fitter, right? And if you can draw this picture out here, and if you know what math is going on underneath the hood there, there's a one-to-one correspondence to what we're doing with a neural network. And so with PyMC code. So this is a neural network function. It takes in our data x, and it subjects it to a series of transformations as listed by the two lines that I'm highlighting. Just those two lines over there. And the other lines of code express that we are unsure about the exact value of W's and B's that are important for making our predictions, and so we put probability distributions on them. And that's all it is. That's all a neural network is. And so as you can see, the neural network becomes a link function between our data and our output distribution parameters. That's it. Okay? So deep neural networks are nothing more than matrix transformations on input data, and they are nothing more than fancy curve fitters. So If someone tells you if someone sells to your company, we are going to sell a very fancy AI based on deep neural networks, first off, you don't have to be wowed by them. You should know underneath the hood, deep neural networks are just transformations, they're black boxes, and yeah, they're fancy curve fitters, all right? If you're interested, you can check out another talk that I did last year at PyData in New York City. That will have more pictures and illustrations inside there. So let's go to the second part of this talk, which is I've hopefully shown to you that deep neural networks are nothing to be scared about. But the more exciting thing here is how we can use Bayesian methods to help inform our design, right? So the question I want to try to pose and then answer is this: how can Bayesian methods help you design more reasonably? And here, reasonably means in a way that doesn't violate common sense as well as common statistical sense, okay? So I myself, being born in Canada, means ice hockey is our national sport. Nobody else can take it from us. We are going to be the world champions every year. My beloved Vancouver Canucks, unfortunately, were defeated by the team that the Boston Bruins, and I live in Cambridge, Massachusetts, which is the supporting team of, supporting city of the Boston Bruins. So I could not wear my jersey, a Vancouver Canucks jersey, to my first day of class because the Bruins defeated the Canucks in 2011, which was the first year of my grad school. But nonetheless, ice hockey, we know roughly how the game works. It's like football here. There's a goaltender, and the goaltender must prevent shots from going in. And that's really all it's about. One thing that we can ask, so if you're a game designer and you're designing an ice hockey game like the NHL series by EA Sports or something else, you might want to ask your players to pick, simulated players inside the game. And those simulated players will have statistics that are associated with them. Say for a goalkeeper, we'll be interested in the goaltender's probability of saving a shot. So I'm going to do a very quick poll over here. So let me set this up. We can quantify goaltender performance by counting the number of shots that were shot against the goaltender, and then counting the number of shots that the goaltender saved. Simple enough, and we take a ratio, right? So in this case, this player, Jake Allen, saved about 90.6% of the shots that were sent to him. So I'm going to put out a question to the audience here. I'm going to give you two more players. Of these three players, who would you call the best goalie? Let's see. How many of you would be... let's wager 10 euros on this. Let's pretend we're going to wager 10 euros on this and ask how many of you would wager 10 euros on Jake Allen as being the better goalie? So 3 people. Lots of data over there. 4 people. How many of you would wager 10 euros on Dylan Ferguson? Probably nobody. Okay. And how many of you would wager on Scott Foster? 1 person. Okay, so we have, based on a poll of the crowd, 405 or 401, right? Okay. And that's already itself a probability distribution, by the way. People voting with credibility. So if you were to present in a game, for example, the end user were to look at this table, how do they make this decision? How can you help them make an informed decision as to which player they should pick, right? Showing them this table isn't really going to work. Maybe what we might want to do is to find a way to express our uncertainty surrounding these 2 players, Dylan Ferguson and Scott Foster. And that is where Bayesian methods come into play, right? So let's start with a very simple, naive model. Let's assume that every player is independent of one another. There's no relationship between the players whatsoever. And we want to model P, which is the goalie's probability of saving a goal. And each value of P is independent from one another. We might draw a picture that looks like this. There are a number of players going into the background of the screen. We model the shots. We model the shots saved versus the shots against as a binomial distribution, shots against being the number of shots trials and shots saved being the number of successes. And we use a beta distribution, which is just another distribution for for expressing uncertainty around probability values, which have to be bounded between 0 and 1. You don't have to worry about the math behind that. But basically, that's what the beta distribution tells us. There is a one-to-one correspondence between this picture and the code that you will write as the PyMC3 person. And I just wanted that to be the main point of this slide. Having looked at that data, we get charts that look like this. With that model, having seen 2 shots on goal with 1 saved, Dylan Ferguson, we now believe, is a player who has the most amount of credibility assigned to a shot saving probability around 0.5, but with a lot of uncertainty, right? Sounds kind of reasonable? Maybe. Let's think about it, though. Given what we know about player human performance in a bunch of tasks for which we've got a population of people who are kind of related to one another, is it really reasonable to assume that Dylan Ferguson is this bad? I mean, if Dylan Ferguson, for example, were an amateur rookie player and not one who's come up through the youth leagues all his life, then yeah, perhaps so. But we know he isn't. He is someone who has come through the youth leagues. He's played in lower leagues. He's got a lot of hockey experience. It's actually kind of unreasonable to assume that this player we expect this player to be this bad. And that's what we're saying here. So let's try to encode a more reasonable intuition about player performance. Well, we can make one thing that we can say is that given the thousands of other players, hockey goaltenders that have come through the ranks, we know that most of the time they will save between 89 to 93% of their shots. So how exactly do we encode that intuition? We do it this way, and I'm not going to go too deep into what exactly the model is all about, but all we're saying is that players themselves follow a population distribution, okay? And we express it by saying that these parameters are drawn from some parental distribution, and they're all shared between individual players. And so there's some terminology there. I'm not going to belabor it, but basically this is the intuition over there. And once again, there's a one-to-one correspondence between the picture that you'll draw and the code that you will write. And the posterior estimates, our final estimates of player performance, actually become a little bit more reasonable. Over here, what we see is those 2 players, the one in blue and the one in yellow, we don't have a lot of good information from the game about them, but we think now, based on this model, that they're going to behave on average like the rest of the players, right? Rather than one being really, really, really lousy. However, we're still quite uncertain about them. So players without much data, they should be considered average, and that's reasonable. But we should also consider them to have high uncertainty, and that's a natural result of doing this Bayesian modeling. All right? OK, so some pointers I want to raise here. First off, we call this Bayesian partial pooling. And that is a way of sharing information between players. And this hopefully is a good anchoring example for you. And so we can impose reasonable prior knowledge. And instead of having unreasonable estimates, now players are sort of centered around the population mean, but they aren't, and so we don't get these unreasonable estimates there. Secondly, I'm sure it's probably clear to designers. I'm not a designer myself, but I know if I'm presented with a table, scientists can look at tables, but they're sort of hard to look at. From a UI perspective, the average user will need visuals, and I think the place where AR and VR comes in here is you can actually design experiences that help the user to understand what this uncertainty is all about. Secondly, we can check models against reasonable prior information, and that's the 2-step modeling example that I had shown you here. And finally, I hope it's clear, probability distributions express credibility assignments, and that's all probability distributions are. Okay? So finally, I'm going to conclude with some epiphanies. Firstly, I came to the realization this year, finally this year, that deep neural networks are just merely an example of a link function between your data and your output probability distribution parameters. That's all a deep neural network is. It's simple math underneath the hood. Secondly, I hope it's clear from that gaming example, if you use Bayesian methods, you can help quantify in a much more reasonable fashion and quantify uncertainty in a much more reasonable fashion, and they can help us then inform the design of whatever we're doing downstream. Finally, if you've followed the talk so far, this is really the thought framework. There's model complexity against informational richness in the model, and if you go Bayesian, you get lots of informational richness over here. But really, at the end of the day, machine learning, linear regression, Bayesian versions of each of these, it's just curve fitting all the way down. All right? All right, so with that, thank you very much, and I hope you have a great rest of Digility.